Look at the density of multi-story arcades across Kampala's skyline. To safely support buildings of this size, engineers rely on concrete. But before a single drop of concrete is poured, construction workers must weave thick steel bars, known locally as matayemba, inside the molds for the pillars and beams. To understand why the steel is absolutely necessary, we have to look at how different materials behave under extreme physical stress. A heavy load forces the molecules inside a material to react. Some materials will bend, some will stretch, and others will simply shatter. This diagram shows what happens when a heavy load rests on the center of a horizontal beam. The weight creates two distinct types of stress at the exact same time. The top edge of the beam squashes inward under compressive stress, while the bottom edge stretches outward under tensile stress. Concrete handles compressive stress perfectly. You can squash it under thousands of tons and it holds firm. But under tensile stress, that stretching force along the bottom, plain concrete is highly brittle. It pulls apart and cracks from the bottom up. This is where the steel bars come in. Steel is exceptionally ductile and possesses immense tensile strength. By embedding steel specifically along the bottom edge where the tension is highest, the steel absorbs the pulling force, keeping the concrete solid and crack-free. Designing safe structures requires matching specific mechanical properties, like tensile strength, to the exact locations where a structure is weakest. To isolate and study how materials handle stretching forces, we use highly elastic materials in a controlled setting. Here we have a standard laboratory spring hanging next to a ruler, marking its initial resting position. When we attach a 1 Newton load to the bottom, the downward force causes the spring to stretch to a new position further down the ruler. A common trap here is misinterpreting the final measurement. In physics, the property we measure is extension. Extension is strictly the mathematical difference between the new stretched length and the original length. It is not the total length of the spring. This diagram shows the exact formula governing this behavior. Hooke's law, written as F equals K times E. F is the applied force, measured in newtons, and E is the extension, measured in meters. The K in the middle represents the spring constant. This is a specific numerical value that tells you how stiff a particular material is. A higher K means the spring is stiffer and requires significantly more force to stretch. By isolating these three variables, Hooke's law gives us a precise mathematical model to calculate exactly how a material will respond when a measurable force is applied. Let's test this logic with a specific problem. A spring has an original length of 10 centimeters. When a load of 4 newtons is applied, its new length becomes 18 centimeters. Pause the video here. Calculate the true extension, convert that value from centimeters to meters, and then use Hooke's law to solve for the spring constant, K. Doing this calculation yourself builds the mental muscle required to separate total length from extension before a test does it for you. First, we find the extension by subtracting the original length of 10 centimeters from the new length of 18 centimeters, giving us 8 centimeters. Next, we convert that 8 centimeters to meters by dividing by 100, resulting in 0.08 meters. Plugging these into Hooke's law yields a spring constant of 50 newtons per meter. Plotting applied force on the y-axis against extension on the x-axis traces a perfectly straight diagonal line. While straight, extension is proportional to force, obeying Hooke's law. Applying heavier loads eventually curves this line. This precise point is the elastic limit. Pushing an elastic material past this limit means it can no longer recover. The extreme force alters the internal bonds between the particles. The spring might not break entirely, but it is permanently deformed. We can also alter those internal particle bonds intentionally using heat. Adding thermal energy makes the atoms vibrate rapidly and move further apart. This weakens the structure temporarily, allowing blacksmiths to shape otherwise hard, rigid metals into useful tools before they cool and harden again. Whether you are heating metal over a forge or calculating the tensile stress on a reinforced concrete beam, mastering these mechanical properties ensures that the structures we build perform exactly the way we design them to.